Well,
Great.
Good evening, everyone. Thank you for joining us for the presentation hosted by the Victorian branch. So we'll have the pleasure of welcoming Dr. Rob Hewson from the University of Twente, even if he's recently welcome back in Australia. So before we start, there's some housekeeping to go through. So the first thing is thank you to all our corporate members who allow us to be able to present all those webinars. So those are the corporate members for the whole society. But also thank you to all the branch sponsors. So a lot of states have branch sponsor, Victoria doesn't, but we don't have official sponsor, but thank you to all the companies who give help in lieu for our events. So at the end, we'll have a question and answer session. So just to make it easy, please use the question and answer button that you will see on your screen and type your question when you're ready to do it. And at the end, I will read the question to Rob and he will answer them. I think that's it. Oh, no. Upcoming. So this is just one in a long series of webinars. We have a very rich program this year. So there's 3 webinars planned for June itself. And we even have program for July. So some are local, but also international speakers. Some information about the society and the members' benefits that will all have advantages. And then some links to keep in touch with the society. And let's go to the heart of the program tonight. Rob?
All right, thank you, Sita. All right, well, I'll just get my presentation up. All right, thank you for listening in. I hope it doesn't interrupt too much of your dinner or relaxation time, but basically I've worked in remote sensing and geophysics for 25 years on a variety of different companies and CSIRO, and also I had 3 years recently at the University of Twente in the Netherlands. And there we were using remote sensing and geophysics for teaching and research in exploration. So just basically what I'm going to cover in my contents, because it's not necessarily a topic that's familiar with quite a few geophysicists, I'll cover some of the background and what I believe are some of the caveats, issues with geological remote sensing. Probably well aware of the obvious ones, vegetation and cover and that sort of thing, but I'll go into some of those details. Operational sensors at the moment, satellite, airborne, and examples of drones. Some of the archived imagery and data products, particularly accessible within Australia. And also I'm going to present the case study I presented at last year's ASCG AEGC in Perth. It covers using WorldView 3, ASTER and HYMAP, and also integrated with geophysics. Do a few case studies on gold, manganese, magnesite, oil and gas and rehab type of stories, with some success as well with those techniques. All right, so some of the issues and caveats associated with geological remote sensing are obvious ones like the atmospheric conditions, illumination conditions, the sun angle, for example, ground conditions, including vegetation cover, the regolith, sediment or soil cover, desert varnish, weather crust, and the sensor spectral and spatial resolutions are a fairly critical part of the limitations and things that have to be decided before one does a remote sensing study. So, atmospheric windows. I'll explain this as best I can. This is basically showing a transmittance versus wavelength in microns. So we're looking at the visible near infrared between 0.4 and approximately 1 micron with water vapor features, CO2. So there's obviously greater transmittance where we have the visible, and then in the shortwave region between 2 and 2.4, we've got some sort of window there joining the CO2, H2O, and H2O absorption features. And then in the thermal infrared, which to some extent is a sort of a frontier area for remote sensing, not as many sensors. However, there are windows there between 3 and 5 microns and between 8.5 and 13 microns, as you can see, with the added ozone feature at about 9 microns as an issue. So illumination conditions, obviously the solar elevation affects the illumination, particularly at higher latitudes during the winter and in areas of topographic relief. So you can do a simulation, if you like, of those effects to some extent with topography if you've got a digital elevation model. And here I've got an example actually of a site in central New South Wales, simulating what ASTER is, looking at 10:30 in the morning when it acquires. And this is a sunlit simulation, if you like. So obviously there's going to be some shaded areas that won't be illuminated by remote sensing. Ground conditions, high water moisture, such as after the day after a rain, for example, will severely reduce your mineral absorption features. So as well as lowering the overall reflectance, it will actually reduce the contrast of the absorption feature of the mica or clay mineral that you're most interested in. So you have to be aware when you acquire data. The effect of the surface, whether it's specular or, as it's called, lambertian, that's where you have bidirectional type of reflectance versus a lambertian, sort of scattered, and that lambertian is optimal. So in the case of airborne surveys, if you're involved with acquiring data, it's best to collect it in a north-south direction to reduce some of those scattering issues. There's obviously issues of obscuring of rock outcrop exposure by vegetation, shadow, lichen, moss. Green vegetation in particular can interfere in the visible near infrared. I'll go into those details later, and potentially mask and interfere with your iron oxides of interest, hematite, goethite, for example. Dry vegetation has a shortwave infrared spectral feature, which can also complicate the interpretation of clay minerals, for example. So here's just a couple of pictures, again, using central New South Wales. And here you have, even though it looks quite open, if you've got an issue with late in the day acquisitions, you're going to have shade. And then, of course, you've got still the issue of potential litter. You might have open canopy, but you might have lichen and moss on the ground. Here you've got some iron oxide scree and soil debris, but you've also got this issue of moss and lichen. Okay, sediment cover, transported cover, if you like. If you've got highly weathered terrain, you're obviously going to have a limit of fresh rock exposure. So understanding what what sort of is the nature of your terrain is important. There's some fantastic papers in the CRC Lean website that cover a lot of information about the interpretation of regolith mineralogy that might be related to the subsurface. Not always if it's transported, but there are some great remote sensing and spectral papers on that regard. And in that way, you can use things like kaolinite crystallinity, iron oxide species that can separate and distinguish between transported versus in situ. Also, the mineralogy of windblown or alluvial cover might be different, of course, from the outcrop and scree that you're trying to target for the subsurface information. However, using digital elevation models, whether it be SRTM, shuttle-based radar information, or LiDAR, for example, that can give you extra information through slope analysis to give you some sort of idea of what is likely to be alluvial, colluvial versus your outcrop. So that might be help you overcome some of those issues, or at least separate that problem. Desert varnish coatings, particularly a problem in parts of Australia, North Africa, in arid regions. So that's where the crust might actually obscure some of the outcrop and scree material with iron oxide and manganese coatings. In fact, there's something in the Pilbara called limonite degraded kaolinite, which is both iron oxide and kaolinite coating on some of the units. So that's a problem which can obscure some of the signatures of interest. Here's an example in actually the Cudamona near Broken Hill. This is where you've got iron oxides coating the scree and gravels, and that's important to know about. So it might actually be in situ, but it would actually disguise some of the mineralogy of interest, for example. Spatial resolution issues, that's very important. Here, example of ASTER versus Worldview 3, two satellite systems. ASTER no longer requires all those bands, but there's an archive of thermal, shortwave, and VNIR for at least 8 years, and 90, 30, and 15 metre pixels. So you can see in this example of a building site, you're not going to see much in the thermal at 90 metres, but you'll get better at the visible near infrared. Typically, I merge the shortwave and the VNIR to a 30 metre image to actually to combine those two. Worldview 3, it's listed here at 7.5 and 1.2. In fact, they're now releasing the full resolution Worldview 3, 3.4 metres, and I think it's 0.5 metre VNIR. So there's 16 bands here, a much better resolution and a panchromatic. So things that can occur because of this spatial resolution issue is that actually we're looking at the actual mixture of, say here we have a house and the surrounds of the house. And obviously 30 metres, it will just be a mixture, it will combine. 5 metres, you'll separate those out a bit more. 1 metre is even better. So that's basically a mixing issue in the data set. However, even though you might increase your compositional mixing as you go to finer, your compositional definition rather will be improved with higher spatial resolution. There will be also probably lower signal to noise for that sensor. Now, the other resolution that's quite critical is spectral resolution. And you're all probably aware of Landsat, the 7 bands being, particularly since the 80s, you've had 7 bands with the band 6 and the SWIR, versus now we have ASTER, 14, and HYPERSPECTRAL airborne systems over 100. And basically these 3 different regions that we're focusing, visible, shortwave, and thermal infrared, are located in these wavelength regions here, where we see the visible, of course, between 0.4 to 0.7 microns. Also, the bandwidth, the narrowness, if you like, the dimensions of the actual sensing band are also part of this resolution issue. So, as I said, hyperspectral is greater than 100. Multispectral, such as ASTER, is less than 100, and so that will affect how you're able to discriminate the clay group versus individual clay minerals like kaolinite, muscovite. So hyperspectral sensing includes Spectral and HIMAP, and also there was a prototype hyperspectral satellite called Hyperion for a while. So if you have improved spatial resolution, you have potentially decreased spectral mixing between different components in the image, shadow, vegetation versus outcrop. But generally you'll have lower signal to noise as you get smaller pixels, and also the narrower hyperspectral bands. Depends on the sensor that you're using. So some brief examples of operational sensors. This is by no means exhaustive, but you've got Landsat, ASTER, Sentinel-2, Worldview 3 as quite commonly used multispectral sensors, and they're visible to the shortwave infrared. Moderate spectral resolution, less than 100 bands. Free in the case of ASTER. Worldview 3, a commercial satellite that you have to make inquiries for actual rate. Generally broader coverage. Worldview 3 that has a 15-metre width to its swath, but ASTER has 60 kilometre versus 15 kilometres swath width. And you can get them from online. NASA, USGS for ASTER, ETA provides Sentinel-2, and Maxar supplies Worldview 3. Now, airborne systems, this is where you'll have to specifically arrange it. HIMAP through HiVista, Spectral, an American company, and you'll be able to dictate the time of year it's acquired and all those features. Higher spectral, spatial resolution, higher cost, of course, and generally a limited coverage, so that you're looking at maybe more mining lease, detailed exploration areas. Now, the new kid on the block is the UAVs, the drone sensors such as HySpecs, HyperCam, and Spec drones in Australia, where they have high spatial and usually high spectral resolution. Again, expensive, limited coverage, and it's been designed more for mining lease areas, brownfields, if you like, and rehabilitation areas. I'll do an example of those. NEO is actually a Norwegian company that produces HySpecs, Telops, HyperCam, and MicaSense is an example of visible near-infrared sensors from sphere drones. So just to summarise all that, if you like, hope it hasn't been too quick, but you can go through this later. This is a pretty typical chart to show reflectance versus your wavelength, visible to the shortwave infrared, and then you've got the thermal infrared. And just a few reflectance signatures, which are not specific to lots of sites, but generalized ones for green vegetation, limestone, dark soil, sandstone, dry vegetation, versus the actual bands, the approximate position of these bands. Landsat TM, there's an extra couple of Landsat bands with Landsat 8. ASTER's 14 bands shown here, and then you've got airborne HIMAP data there. And that's been available since 1998, and there's more spectral satellites now. So yeah, you've got that compared to Worldview 3, which is a new multispectral satellite with 16 bands. So I've also mentioned the spatial resolution in this. So as I said, Worldview 3 has now released the highest spatial resolution VNIR, and 3.4 metre shortwave infrared data sets. And something which I won't go into because we've been waiting very patiently for a long time, these hyperspectral satellites that the Germans, Japanese, possibly Americans, there are prototypes, there are military ones, of course, but the ones that we can access for civilian use. Hopefully we'll have data released later this year or next year. And I think it's approximately 30-metre pixels, most of them. Fairly narrow flight orbit swathe widths. Might only be 15, 30 kilometres at most, but they will be eventually coming on board to help us give us, something like the HYMAP data sets with coarser pixels. Okay, so how does that relate to geology? This is a very broad brush talk, of course, but iron oxides, hematite, goethite, jarosite, can be easily or more easily mapped in the visible and infrared region between 0.4 to 1. Shortwave infrared is good for your clay minerals, phyllosilicates, kaolinite, alunite, muscovite, amphiboles, sulfates, and carbonates. Whereas the thermal infrared is particularly useful for the silicates, such as quartz, feldspars, garnets, pyroxenes. Okay, just a little bit on a background of other sensors, such as Landsat 8, and these are basically the generation of Landsat MSS. It's been around since the 70s. We have Landsat TM since the 80s, Landsat ETM+, and then Landsat 8, which is being used now, and it's got it's got two thermal infrared bands. So you can actually see, you probably realise the 30-metre pixels of Landsat, but panchromatic's quite good, and it has, of course, thermal bands, as I said. So ASTER versus Landsat, you've probably seen this before, but basically we're getting all these extra bands now to distinguish particularly argillic clay-bearing minerals, propylitic minerals, and with the thermal we've got the silicates identified more easily with the thermal bands of ASTER compared to the limited 7 bands of Landsat 7 and 5. HYPERSPECTRAL, that's pertinent for your airborne systems such as HYMAP and Spectral. This is just a cartoon showing you basically looking like a cube of data. X and Y, and the Z is your different bands, and 100 or more different bands, so that you're actually looking at all these different features, whether it be atmospheric, soil features, water features, vegetation, and hopefully some mineralogy is thrown in too. So that's just a broad summary of these things. And HYMAP scanner, it's been around since '98, and of course there are others since then. An Australian system, and that's got 4 different detectors, narrow spectral bands, and high spatial resolution, so over 120 bands. Okay, so to compare ASTER and HYMAP, for example, I've shown an example of some area that I worked on in the Coonamoona, Broken Hill. This is the project I did with the South Australian Geological Survey. And these are the ASTER interpreted scenes that we looked at. And just there you can see the red dot. That is where I've got a close-up here down below of looking at a cross-section of some salmites and phibolites and also some retrograde shear zones. Here I have like a transect where we actually measure on the ground with ground spectrometer, and these are, for example, by comparison, the ASTER pixels. So the small yellow ones are equivalent, if you like, to a HYMAP pixel, because HYMAP was acquired by the New South Wales Geological Survey over the Broken Hill block, and a study was done by CSIRO to do a comparison. So if we did a comparison of like the spatial and spectral signatures, then we're actually looking at the much coarser spatial issues of ASTER compared to HYMAP, but we're still getting a shortwave infrared signature that's highlighting on a coarse level, the ALOH or clay features. However, if we look at the HYMAP issue for the same small area, we're looking at 3.5 meter pixels instead of 30. And we're also looking at many more bands to distinguish these mica versus amphibolite type signatures for these units. See, this was geology map at 125,000 scale. So it shows basically, if you've got the money, it's terrific to get hyperspectral airborne. But if you don't need that resolution, then ASTER will give you some of that information. Now, you can get that data quite easily from the Earth Data website, and here it is here listed. First of all, this website here is a JPL NASA website. It'll give you a lot of information of documents, publications, background information, both for geology and environmental. This is the search engine that I recommend for actually extracting the scenes. It's actually a fairly well-polished, custom-oriented sort of website now. So you don't just get the low processed levels, you get the second and third order processed products, so just surface reflectance. The atmosphere is taken out or by modelling, or you actually have the temperature effect removed for the thermal data. So you can order a lot of different products via this website for your scene, and you can just put in a KMZ or a shapefile, and you can target your particular area. Now in Australia, we've been lucky to actually have sorry, this has jumped ahead, a map product for the whole continent interpreted. That's actually covering 17 different products, and these were interpreted with GA's help, Tom Cudahy, Mike Cagetta, and a few others. And sorry, this is jumping ahead. Yes, so it's somehow freezing ahead, but anyway, you can see that later. You'll actually have 30 megapixels of products like this. This is the ASTER interpreted quartz index. Obviously, you've got the Simpson Desert, the Great Sandy Desert, with an increased amount of quartz sand covered. And that's available via the Ozscope Discovery Portal. And there's also that website there that will give you your extra information, documents, and assumptions that go into that processing. And this is another website there that should be useful to give you that information. So you can actually download this data for free from the Ozscope portal, along with lots of other data, geophysics, topographic, lots of other information. And an example of what you can do with that in obviously an arid area. In fact, it's just in the northern Flinders Ranges. This is Mount Pheasant, which is often used as a test site. And so various products compared to the 100,000 map sheet there. It's quite successful there in this semi-arid terrain. Okay, I'll just cover rather quickly the investigations I've been doing with the both Well-3, ASTER, and HYMAP over the Haib Cu porphyry deposit in Namibia. This was also done with work done by Manuel Jinkaka of Malawi, who's was a master's student and did quite well at doing this, and working also with other colleagues and the Namibian Geological Survey. Presented last year at that Perth conference, as I said. So here's the area, Worldview 3, visible natural colour. It's in the southern part of Namibia near the Orange River. And as you can see, it's just perfect from remote sensing terrain, very exposed. It's got some old workings shown there. Limited vegetation cover, moderately dissected, but not too mountainous or anything. Yeah, it's a good remote sensing target, of course, and with, it's got a canyon nearby. It's worth seeing. Precambrian porphyry deposit, particularly in a quartz feldspar porphyry unit. It's quite a large copper resource developed by Deep South Resources. Yeah, and it's a relatively compact deposit, 2 by 1 kilometre, and going down deep, looks like. So the actual square that you see there, that's the actual prospect itself of interest. And here's the course geology shown there. So it's approximately in this region here. It's got some alluvial cover, but it's not an issue here. This is another map showing this actual hub prospect region here. So it's contained within this quartz feldspar unit, and occurs within the area shown, yellow and red. Now, this company that was doing consulting produced products from the airborne HYMAP data a few years ago, and this is one of their figures. And you can actually access that on the internet, showing this prospect area. And actually, quite often they use red, green, blue composite images of different minerals interpreted from the remote sensing. Red is the sericite or mica, green is interpreted as the chloride, and they've interpreted the blue areas according to some classification scheme, the recent sediment cover and the Karoo sediments. So what I was trying to do actually was trying to see if we could get the high resolution or some of the products that we detect with HYMAP with WorldView 3. And I used the HYMAP data that was quiet in a resampled mode. And I also did the same with ASTER. So here we have this prospect area in green, and we actually have the geology overlaid. Now we're getting a much closer, clearer fit because of the spatial resolutions better with WorldView 3. We're getting overall similar sort of anomalies with the ASTER, but you'll notice these areas here are anomalous, and what we actually have is an issue of some shadowing, illumination effects from the shadows of the terrain. So it appeared that the WorldView 3 gave generally better results and was more comparable to the HYMAP airborne data sets. So this is a ILH means mica, muscovite, a clay type of information product, which could include kaolinite and also muscovite of different composition. And here I've actually looked more closely by thresholding the abundance to give me more isolated, more confident type of interpretations of kaolinite. Argillic could also mean alunite, which is another mineral of interest for copper porphyry bodies. And that's approximately in the region of this hub copper porphyry body here. The radiometrics is shown here as a ternary image. Not showing, showing some units which are discriminated. The geological units are separated, but it's not as clear cut. The alluvial is fairly broad in having more uranium anomalies here, but nothing highly distinguished in this area of the hub copper porphyry deposit. Looking at the magnetics, in fact, Emmanuel did an interpretation of the first vertical derivative magnetics using an automatic lineament program, and came up with these black lines here. Underneath, I've got the HYMAP, or sorry, the WorldView 3 resampled from HYMAP. And this is the actual magnetics itself. So you're actually seeing how he's interpreted the lineaments, because it's a structurally controlled. They suspect there's some structural control to this copper porphyry body. So that was seen as something to undertake. And here I've done an integration product actually using both WorldView 3, clay content, iron oxide or ferrous iron, rich amphibolites and MgOH minerals such as chloride, and also the magnetics in blue. So that shows interesting sort of features. So we're actually able to see the actual structures from the magnetics and how they compare with some of the mineral features here. So I've looked at this region here of the radiometrics, and I've actually looked at the potassium in particular. I think that's actually probably a highlight here with the potassium rich core of the copper porphyry showing up. And I actually had a go at actually thresholding and masking that according to the mineral content from the WorldView 3 data. And there seems to be discrimination of the mica or clay content according to the potassium concentration. So that's a potential integration product that you could have a go at. So I've got potassium versus the abundance of clay shown on the x-axis here. And as I said, this is the HYMAP product produced by these consultants, and they've actually identified IP and copper geochemistry anomalies where some of these HYMAP alteration vectors have appeared. So showing that the geophysics is useful to follow on from the reconnaissance type of remote sensing processing. So summary, the conclusions, like as I mentioned in this talk, I'll leave that for you to read later on, but it's basically a mention how that integrating the geophysics with the shortwave infrared mineral products can be useful in this case. Unfortunately, we haven't done field work in research activities. It's something that we'll like to do later on and provide that information with the mining company and the Namibian Geological Survey. Another case study, and I must admit I'm not closely related to this except that I helped with some of the ASTER geoscience maps, but Carlson Laupkamp of CSIRO did this work with Tom Cudahy, and this is actually using these Australian-wide mineral maps, and it looks like it's quite a successful case study in Northern Territory, looking at iron oxide, copper gold, and gold alteration associated to bodies in quartz veins. So the product from the ASTER maps, the magnesium OH or amphibolite like and chlorite group, and that can be separated between the carbonate anomalies too. So it's identified more clearly the chlorite alteration areas here, which are of interest for interpreting this body. Another case study I worked on personally was using ASTER and HYMAP at the Woody Woody mine in the Pilbara. Here's the boundary of where we've used ASTER, and this is actually the mine side of Woody Woody where we did a close-up HYMAP study. Here's the detailed mine geology here, and here I've actually produced something that was useful where you combined the ASTER silicate information in blue with the HYMAP ferric iron information in green, and the ASTER quartz information is in red. The HYMAP ferric information is in green, and then we've got the HYMAP carbonate information, and that's because the manganese seems to be associated with carbonate, which has had hematization, and so combining these together with the topography gives you an idea of where it's outcropping, and that matched nicely with previous control with the geology. Also, there was integration studies done with the thorium product, because that's a good way to try to separate out the ferrocrete type of iron, which is often associated with thorium. And then by doing topographic modelling, you're able to target those areas that are outcropping versus those that are more likely to be regolith and the floodplain type of areas. So one of the main outcomes of this was that it was actually promoting the further processing of 100,000 map sheet of HYMAP, because it was seen as being much cheaper to use the HYMAP to get these targeted areas, which then follow up with more expensive hoist EM surveys. And so it was, again, you know, where you could do reconnaissance surveys with remote sensing and then target those areas later on with your geophysics. Another area that looks like it's been successful is the South Australian manganese metal project, or magnesite, in a deposit near Lee Creek in the Flinders Ranges. And I wasn't personally involved, but I hear from Alan Major that was quite successful. And it actually enabled them to give new exploration targets for the magnesite exploration project. Rehabilitation monitoring, that's an obvious sort of thing that remote sensing can do, where you actually can identify the health of the vegetation and maybe classify its nature. In particular, they looked at the woody cover component of the vegetation using a drone, a VNIR drone, to actually highlight the areas of regrowth. And for example, here, 2014, 15, 16, they did flights with this UAV drone, and that was successful in actually monitoring this increase in rehabilitation, which is what they'd obviously need to do. So you're able to monitor the change with multi-temporal drone measurements. And last one, I'll just briefly go through examples of using remote sensing for oil and gas. This is from Carlos at the University of Campinas in Brazil. And he's had quite an interest and been active in using spectral sensing for seepages and for methane discharge, using various different remote sensing surveys. In this example here, I'm looking at the feature in the shortwave infrared at 1.7 microns, and that's equivalent to the Worldview 3 band 12. You can see this band 12 here of Worldview 3. ASTER has one band, but it's fairly broad, so you'd want to have higher spectral resolution. And you can see this here, laboratory spectra of various hydrocarbons. So you can actually see this feature here at 1700, and the grey is the Worldview 3 band 3 feature. It's potentially of use to identify these seepages here. So if you resample those, you can actually see that there will be some diagnostic feature may be discernible. And this is actually being applied here in a seepage study area of Brazil. And in the areas shown here, they actually identified these as the actual products with the band 12, I'd imagine. The seepages are in blue, and the circles here highlight what's identified in the field here. So these are being measured and analysed for hydrocarbon content. So that's been established and proved that way. So again, so looking at the spectra, you can see these features for these carbon-hydrogen bonds, which give rise to this absorption feature. And basically we have seepages coming from the source up to the surface. And there's also, should be noted, there's other ancillary type of regolith chemical effects of this seepage, such as the increase in iron content, and of course changes in the vegetation cover as well. So again, it's part of the same story. I'll leave you also to look at this. This is summarising the outcome. So it's seen that Worldview 3 is potentially useful for such seepages if the pixel size is sufficient to pick them up. And of course, we're looking at 3.4 megapixels now with Worldview 3. Okay, in summary, basically, I think I'd like to say that if you take into account all the caveats and limitations, acquisition time, sensor performance, ground, geological conditions, then it's possible to have success with remote sensing. But it's critical to have the appropriate sensor and technology. And one thing that's changing rapidly is that there's new toys coming all the time, and there'll be hopefully hyperspectral satellite sensors down the track as well. So and also I'd like to say that typically the interpretation is improved with the integration, of course, with geophysics and other data, and it might actually be something that's done before you do the more expensive geophysical surveys as well. And of course, finally, it's not always guaranteed, but if you can look up case studies for that area and those techniques, then that might be useful homework to help make it worthwhile to try. Thank you.
Thank you, Rob. Thank you very much for your talk. I hope everybody enjoyed it. So I have a few questions for you now. So first one is, do you think that LiDAR technology will eventually become price competitive with aerial photogrammetry and replace it?
That's a good question. I'm not a specialist on LiDAR, but I think it can be very useful to give you your geomorphology and landform information. But as to the price, I'm not sure. I've heard some stories that there is going to be satellite-borne LiDAR technology. I don't know the status of it though. So I hope it will be competitive. Yes.
Next question from Dave Alex. Great talk. Could you comment on the effect of topography on measurements?
Oh yes, that's well, it depends on the sensor. Sometimes it's critical to do rectification of some of the satellite data. For example, ASTER can be, you can obtain auto-rectified ASTER imagery to improve your accuracy in high relief areas, mountainous terrain. So yeah, that can be important. In Australia, I found that the topography hasn't been a big issue. If you're in a gully or a gorge, yes, you'd want to be as accurate as you could spatially.
Next question from Kane Bauman. Have you found that there is an optimum spatial resolution to avoid noise while still minimizing mixed pixels?
Sorry, could you repeat that, please?
Is there an optimal spatial resolution to avoid noise while still minimizing mixed pixels?
Right, well, I think that's almost an engineering question, and I think the improvement of signal to noise is getting better with time. There have been estimates that, for example, a hyperspectral airborne sensor can have resolutions of 400 to 500 to 1. Of course, you'd have to be aware of the reflectance value, whether it's a low reflectance target or a high reflectance target they're using that on. Whereas ASTER was between 1 and 200 signal to noise, and that at a coarser pixel size. So it actually involves a lot of things to do with the ability to do the atmospheric correction, the engineering and the type of sensor. There's different types of sensor, push broom and array. So I think it's improving with time. So I can't give you a cut and dry answer about the best pixel size. I think you have to test it out as well. If you're going for a very subtle feature, then you really want the best signal to noise. And a lot depends on the size of the outcrop. The actual, like I showed examples of fairly thin beds at Broken Hill. You actually, you want high spatial resolution to be able to distinguish those, but you'd want it to be higher signal to noise too.
So next question from John Taylor. What handheld spectral units do you use for field spectral validation and or verification studies? In what wavelengths does it cover?
Look, I have used the analytical spectral devices, field spec instruments over the years. Sometimes I've actually just collected the samples and taken them back to the lab so that I can measure them more quickly between the visible to the shortwave infrared. I've also seen demonstrated the new Spectral Evolution handheld spectrometers, and they look fairly good too. I'm not up to date on the latest spectrometers that are around. There's more and more coming out, of course. Thermal infrared's a harder area to have a field device for. And again, I prefer to actually take the measurements, take the samples in the field and bring them back. And I've used a design and prototypes micro FTIR in that case.
So from back again, you mentioned that remote sensing in MIR-TIR wavelengths range is a frontier. Is there any promise in acquisition of this range, of this wavelengths range, for mapping hydroxyl-bearing minerals and carbonates, especially considering the very strong water bend at around 3 micrometers?
Sorry, well, it's definitely a frontier area in the mid-infrared between 3 and 5 microns. Yes, and I've only known of some research instruments have been acquiring data over there, such as CBAS. And I think they're very broad modus bands there. But the thermal infrared between 8 and 13 microns, yeah, there's the issue of an ozone feature at approximately 9, but we were able to get fairly good signatures between 8 and 12 microns otherwise. You'd want dry conditions, definitely, because water is the enemy. It's where you will actually have a closer to a black body type of behavior of the surface. So you want dry conditions. Even green vegetation contains enough moisture to give you a black body. So you want dry conditions in those areas. But yeah, it's a useful area for mapping those minerals you can't map in the shortwave infrared.
Another question regarding infrared. So taking you out of the field of geoscience, I know that during December, January, several geophysicists found themselves closely involved with the massive bushfire in New South Wales. A critical task was trying to predict the position and direction of travel of bushfire fronts. Due to intense low smoke, the use of helicopters of geodesic observers had to be terminated. Are you aware of an evolving application of drones with thermal infrared sensors to efficiently and safely map bushfire fronts where smoke preclude other methods?
Not of drones in the bushfire scenario. I'd imagine the winds and the temperatures could be quite challenging, and of course, you know, they often don't fly for longer than 30 minutes. I have heard that HIMAP has flown at altitude above some of these bushfire areas because the shortwave infrared region can pick up the very high temperatures as you go down to shorter wavelengths, such as the shortwave infrared. You need to have much higher temperatures to detect them, and they can be possible with an airborne system like that. But I'm not familiar with drones. I know that they're improving their diagnostic ability in the thermal infrared, but I don't know specifically for bushfires.
To use high-resolution spectral signatures to remove the effect of shadows and easily separate vegetation and litter cover.
What was that last part of that question?
So, possible to use high-resolution spectral signature to remove the effect of shadow and easily separate vegetation and litter cover.
In areas of cover. Yes, well, it is a problem. You can use ratios to some extent to remove some shadow effect, illumination effects that are differences. But no, it obscures the ground. Then there's no way you can really extract that. You can use unmixing techniques if you've got a very good signal to noise and you've got a mixture of, say, a clay signature and on the ground, and then you have the canopy in some of the pixel that is green, chlorophyll rich, then you'll about be able to separate the VNIR affected vegetation signature from your clay affected shortwave signature. So in a pixel, you might have a mixture of those two, and that's a question of the processing techniques that you use.
Next one. Would VNIR, so 300 to 1,000 nanometers, be suitable to compute grain size on carbonate beaches?
What was the wavelength range? Sorry.
300 to 1,000 nanometers.
Right. I'm not familiar with VNIR for grain size. I know that it's sometimes used for soil discrimination, but I'm aware of grain size effects in the shortwave infrared for carbonates, and also in the thermal infrared there are features for both quartz and carbonates affected by the grain size. There's changes in the depth of the absorption features and so forth, but not in the VNIR.
The next question also concerns VNIR. So with VNIR on drones, is atmospheric correction needed?
I'm not as familiar with drone processing as the airborne and satellite. I'm not sure if they're flying at fairly low height, altitude. In fact, I think it's very limited because of the restrictions with airspace. So I don't think there's too much of an issue with atmospherics, but possibly in tropical areas, humidity would be a thing you'd need to correct for the water vapor content.
Next question. What are the kinds of mineral percentage, like composition required to lock in the types in this analysis?
What percentages of various minerals you need to be able to identify the composition? Is
I think so.
Yes. That's a difficult question in itself too, and might depend on the sensor, the pixel size, and the spectral resolution. Yes, I think I see this as more of a semi-quantitative tool to actually say we're getting quantitative in our abundance. I think that's pushing it, and of course you're only looking at a wave range. So if you've got quartz, you need the thermal infrared. If you're just looking at the shortwave infrared, you will just be looking at what's diagnostic in that range there. So it's the percentage of the diagnostic features in that wavelength sensing, rather than its absolute mineral content. I would probably want less than 40% vegetation cover to have a chance at sort of diagnostic interpretation of minerals, and you'd want to hope that it's not wet, it's not damp. If it's wet vegetation, that might also restrict its identification.
So do you think the introduction of satellite hyperspectral data will be a step change in the field?
I think it's going to be a process of getting it researched and having case studies developed. I believe that some of the hyperspectral sensors are more geared to commercial geological mapping, than others, more in environmental mapping, but both might cover the visible to shortwave infrared. And also there's an issue, you have a narrow swathe. So if you're looking at a regional area like you try to do with ASTER or Landsat, you would have to mosaic all these different strips of orbital data to produce probably a useful product. If you've got a very small targeted area, yes, I'd say that it's going to be useful, but I don't know the latest timetable. I think it's still a few years away before it's available for the civilian user.
So 2 more questions. So which method would you recommend if the area was covered with jungle and rugged fields?
Wow. I've used radar, ASR radar. It's an airborne multipolarimetric radar sensor in a temperate rainforest in Tasmania. And there is, especially the longer radar bands, such as L and P, can penetrate the canopy. It's got a high resolution as an airborne system. It's useful that way. I think it is difficult with there possibly geobotanical things to examine, and that if you've got maybe multiple VNIR bands such as Worldview 3 and Sentinel-2, you might see differences in the NDVI, the vegetation index, and some of the characteristics, and you might be able to combine it with LiDAR, the ground penetrating LiDAR that goes to the ground surface rather than the treetops. That's a way to actually look at the counts from the ground. So using a high resolution LiDAR and VNIR might be useful.
Last question. So how often the free ASTER images get redone? I mean, suppose reprocessed, and do they always end up on the same beams if they get redone?
The question is, how long does it take to process the ASTER data?
No, how often they get reprocessed?
Oh, I'm not aware of the new versions that the differences that have come on board. I haven't checked it lately. I know there were some changes to the processing, the level 2 surface reflectance, surface products. But as far as I know, they've been fairly constant recently. Yeah, I mean, I still rather do comparisons on the ground. Ideally, have measurements of samples of a large area to help with the interpretation.
Sorry, Rob. Actually, clarify this question. He was meaning how often do the image get reshot?
How can the image be, sorry?
How often do the images get reshot?
Reshot, oh, sorry. Look, I think they've collected multiple acquisitions of ASTER in the first 7-8 years that you have the shortwave infrared. I think they've been continuing to collect VNIR and thermal data up until recently, if not currently. So I know I think there's multiple coverages. It's every 16 days, I think, that is potentially able to reacquire over a site, such as like Landsat, but it's not always acquiring new data. It's actually trying to get the best seasonal data for the whole globe in terms of coverage, dry season, for example. So I think there might be multiple acquisitions for different seasons and dry seasons. I couldn't say how often. It depends on the area too of interest.
Thank you. So this is the last question from myself. What is your depth of penetration? What is the depth of penetration of the signal you receive? How much? Where is it? Where is the data coming from? A few centimeters, 10 centimeters.
So for just the visible shortwave infrared, it's the top surface, it's the micron. So we're doing a detective work in interpreting from there down underneath, of course, but it's a surface mapping technique. You might see slightly more in microns with the thermal infrared, but no, it's very much on the surface.
Thank you very much. So that was the last question for tonight. Thank you very much, everybody, for attending our tonight talk. Thank you, Rob, for your presentation. I think it was very well received. If you'll check the chat, you'll see compliments for yourself.
Okay. No, glad to fill people in.
Well, the next talk will be very soon on the 2nd of June, and also an interesting subject, forensic geophysics. So have a good evening.
Thank you.